So it might be the dual tautological bundle. There's a basic section. Okay, and it's just going to be S of call this gamma T times a plane over gamma T SW. Now, that should be essentially F. Now, there are various intriguing things. First of all, this gives you, in some sense, the universal solution to this sort of bigger hierarchy. KdV is a sort of special case of this. KdV is a sort of periodic case. In fact, there's a sort of smaller Grassmann you can use, which is just the modeled on the loop space of SL2 or GL2. But you see, somehow the ingredients they're sort of there. Got the circle action. I should say, now that we've sort of seen this a little bit, the Virasoro action and the KdV flows don't necessarily commute. The fact that they sort of solve the two are linked here is a sort of very particular case of the, it's very particular to that particular solution. The other thing I wanted to say is there's already Riemann surfaces here, but they're completely different. So an individual Riemann surface will give you a solution. These quasi-periodic flows, basically. So you define the plane W to be H0. You choose a line bundle. You choose some trivializations to make things live in L2 of the circle. And you allow poles of infinite order. I mean, unbounded order at a point. And that gives you a plane which sort of fits into this formalism once you've chosen the right coordinates. The action of gamma T is basically just acting on transition functions for the line bundle at that point in your chosen parameterization. Okay? And so it gives you, in fact, a flow of line bundles on the Riemann surface. And but from that, using this formalism, this function tau, which in this case is essentially a theta function. So a theta function gives you this solution. So the Riemann surfaces are already there. On the other hand, the one that comes out here is completely different. It has no link to anything. But it would be nice, the matrix integrals, linking the matrix integrals, and you've got some elements here. You've got a determinant bundle. So, you know, for example, if you had a Fredholm operator, you're getting close, your volumes, things like that. But the link to an infinite graphs. On the other hand, this graph picture, once you see the integral in coordinates, you sometimes wonder if this Kontsevich, it's not a statement about the moduli of Riemann surfaces, but it's a statement about trivalent graphs. Right? Anyway, so thanks for your patience. It's been fun. And
thank you for all the lectures.
Oh, it's
spending time here with us.
well, it's been a pleasure. Yeah. Anyway, thanks for inviting me. It's always fun to come here. A bit long in the airplane, but otherwise, great fun. Thanks. Any questions? Or? Hmm?
Is there a combinatorial model for BG in general?
For
BG for other groups?
Oh, for BG, for other groups. That's an interesting. Well, I mean, there's certainly there are a whole bunch of models for BG, right? I mean, starting with Will Milner's original construction. They're sort of all, you know, in the same ballpark, basically. to make things contractible, you have to be able to sort of shove things off to infinity, basically. So you get some sort of infinite sequence. Here, it's very particular. It's also a cheat, right? I mean, it's not quite free as an action. Yeah. Could you do the same with I mean, I suppose you'd just take values in G, and you'd have, I mean, you don't have really good coordinates in an arbitrary group. Well, I suppose you do. They're called matrices. But
This particular is a special case of a more general conjecture called Virasoro conjecture.
Yeah.
So this method, I mean, how much, I assume can't be modified in any way to, I mean, what is some special cases of that are like, probably not.
no, it's not.
So what is,
I don't know. I mean, it's yeah. No, you're right, though. The Virasoro, the general. The general conjecture is I suppose from the point of view of integrable systems, you're seeing somehow this Virasoro is picking out the which plane in the Siegel-Wilson-Grassmannian to orbit. I mean, so from that point of view, if you had a more general operators, maybe you'd see it that way. Like I said, it's one very particular plane, and it's almost, I think, characterized by the fact that zero annihilates things. So maybe that's.
I have one more question. So you define the volume of the moduli space you
Yeah.
integrated in dimension. Now there is one more metric on the moduli space called the Y-Peterson metric, and using that you can define the volume. I mean, are they related?
Well, it's interesting because I think it'd be a different vol. I mean, here it's obviously is a different. I mean, here it's using this sort of Strabel picture, but I believe that there's a sort of alternate proof by Mirzakhani.
The Mirzakhani is
Yeah,
uses,
and she uses the Weil-Peterson. Yeah,
so that is a totally different proof, right? From the, I mean,
it's a very different proof. Yeah, yeah.
But it's sort of retains. They also give some relation on the volume using the
Yeah.
and then
Yeah. I mean, she again has these coordinates where she's looking at sort of geodesics on the thing and sort of measures how much they twist and things like that. And so similar in spirit. But somehow getting beyond the recursive, I think, sort of in understanding what's going on, I think, is the sort of challenge. Okay, well, thanks again.
So now again, you have this V, you have this Xi, and we have this manifold V cross R with the symplectic form V to the T alpha, which you can solve. So if we started with V,
So if the AN are all continuous in measure and there exists a subspace, sorry this is very technical, but when we get to amenable groups and Foldner sequences, I'll just say this follows from this theorem. So I think it's important to write that up so you can see the kind of assumptions we've got here. I'll call that star for all f in D. Then star also holds for all f in B. If the operators are all continuous in LP, then this is not the ergodic maximal theorem yet, I don't think. Oh, no, it is. Right. Okay. So you get this maximal inequality that A star F in P norm is dominated by constants Fp. It's a bit of a marathon, but basically you have these associated maximal functions. Provided this holds, that's like a convergence in measure, that the measure of the set of x where A star F x is greater than or equal to A, the norm of F is less than dominated by this C alpha. C alpha is a function which is left continuous and goes to 0 as n goes to infinity. Then it's sufficient to check on these functions in D, and then you get the result for all of LP. The proofs of these will be in these notes that I put up on the web. And so what we'd like to do is apply these now to the operators A. And that gives us a weak maximal inequality. And so this is the max. This is the maximum value over n of all these averages, right? And it says that that converges in measure. So there's a weak inequality that is dominated by F1. So anyway, I've got some details of the proofs of all these in the notes, and I don't think it's profitable probably to sort of do a rather technical proof here at the moment. Oh, sorry, that's the one I didn't mean to rub out. Oh, it's gone now. So the corollary to this theorem is for 1 less than or equal to p less than infinity, and for all f in LP, A and F converges so it converges not only in the LP and pointwise. Right, so that's my third ergodic theorem. I've got one more ergodic theorem to go. Which is the Horevich ergodic theorem. So I'm going to So what I've tried to show you here is that these ergodic theorems have become a really crucial part of a lot of operator theory, and I mean the link with maximal inequalities and weak convergence is really at the heart of a lot of current modern harmonic analysis, I think, and it's generated a lot of well, we've heard talks this morning already about what about modern harmonic analysis methods using maximal inequalities, and I think a lot of that has come from this. So my last ergodic theorem, which I decided to put in later and is therefore on a different page, is the Horevich ergodic theorem. There we go, found it. So so let's supposing we have x, b, mu, t, where t is a non-singular. Well, that means that mu composed T is equivalent to mu. They're not necessarily equal. Therefore, we have Radon-Nikodym derivatives. d mu composed T to the K d mu. So the theorem says with non-singular